Hello everyone, welcome to the Study Jam session 2. In this session we are going to cover some very important topics of DSA like recursion, backtracking and greedy algorithms. And in the session 1 you have already learned introduction to data structures and you have seen various data structures like stack, queue, linked list. And you also have learned about the STL library of C++, which is very much used in competitive programming, which makes our task easier. So in this session we are moving on to the DSA part and learn some algorithms which are very frequently used like recursion and greedy algorithms. So moving on, these are the topics to be covered in this session: recursion, backtracking, greedy algorithms, and finally we will look at hashing techniques, which is not so important. Hashing techniques is almost nothing but the map which you have learned in the STL library. So we would be focusing more on recursion, backtracking and greedy algorithms. And hashing techniques, it's we will just know about it and we will move on. So coming to the recursion, we will look at what is recursion, then we will look at what recursive trees, and then we will go for how to identify a problem based on recursion. I mean, how to identify whether a problem can be solved using recursion or not. Then we will look at some problems based on smaller input and problems based on choice and decisions. I have actually classified the problems based on recursion into these two types: smaller input problems and choices and decision making problems. So we will look at what it is clearly. I'll explain you clearly what it is. So moving on. First, coming to what recursion is. I hope you are aware about recursion because you have done your C programming course. So recursion is nothing but the process in which function calls itself. A function will be calling itself again and again. That is what is called recursion. And a recursive function solves a particular problem by calling a copy of itself and solving smaller subproblems of the original problems. So you might have heard about the factorial program using recursion or Fibonacci using recursion. What we will do in these cases? We will just call the same problem on the smaller input. The same copy of the problem will be solved. Same copy of that function will be called, but on the smaller input, right? So that is what this sentence means. And a recursive stack is maintained to handle the multiple recursive calls. I'll explain what it is. And the condition where recursion stops is called the base condition. So coming to the recursive tree, this is called the recursive tree. See here, the Fibonacci program is written. If n is equal to 0, return 0. What is this? It's the base condition, right? So when value of n becomes 0, it should be returning the value 0 because Fibonacci of 0 will be 0. And when n is equal to 1 or n is equal to 2, this is the end, right? See, because if n is equal to 1, you can't do Fibonacci of uh, n minus 1, n minus 2 because it would be negative. So this is the smallest possible case. Like this is the end of the recursion. We should stop here. We can't go beyond this. So this will be considered as the base case. And if n is equal to 1 or n is equal to 2, we will be returning 1. And in all other cases, we will return Fibonacci of n minus 1 plus Fibonacci of n. Now let's look at how this Fibonacci program is working. This is the recursive stack which is maintained by the compiler or the operating system to just handle this recursive calls. Initially, main function will be there, which will further call this Fibonacci of 5. Then Fibonacci of 5, what does this do? When the execution reaches the end of the line, that is, return Fibonacci of n minus 1 plus n minus 2. This will make a call of Fibonacci of 4, right? Now Fibonacci of 4 will be executed first. So Fibonacci of 4 will be executed. What does that do? Fibonacci of 4 again makes a recursive calls on Fibonacci of 3. Fibonacci of 3 again makes a recursive call on Fibonacci of 2. This is the base condition which we have written. When n is equal to 2, we have written to return 1. So at this point, this will return a value of 1. Now Fibonacci of 3 continues its execution. Fibonacci of 3, what does that do? Fibonacci, it calculates Fibonacci of 2 plus Fibonacci of 1. Right. This part of code is executed. Now this remaining left out part will be executed. So this Fibonacci of 3 will further make a call of Fibonacci of 1. Now this is executed, it will be popped out from the stack. And Fibonacci of 1 will be returning a value of 1 again. So this is also popped out. And 1 plus 1 will be 2. So value of Fibonacci of 3 is 2. And that will be returned to Fibonacci of 4. This will be popped out from the stack. Okay, got it. So Fibonacci of 4 executed, it's half of the part, right? Fibonacci of 4 will execute Fibonacci of 3 plus Fibonacci of 2. This part is done. Now this part is left out. So Fibonacci of 4 again makes a call to Fibonacci of 2, and that will return a value of 1 to Fibonacci of 4. So this is 2, this is 1. So what is this value? It's 3. Fibonacci of 4 will return a value of 3 to Fibonacci of 5. And what is Fibonacci of 5 actually? Fibonacci of 5 is Fibonacci of 4 plus Fibonacci of 3. So this value is 3 and this is not yet executed. So plus Fibonacci of 5 again calls Fibonacci of 3 and Fibonacci of 3 again calls Fibonacci of 2. At this point, this returns a value 1 and Fibonacci of 3 will again call Fibonacci of 1. This will also return a value 1. So this value will be 2. This will be returned to Fibonacci of 5. So 3 plus 2, it's 5, right? So this is how Fibonacci of 5 is calculated in this recursive function. This is the recursive tree. Fibonacci of 5 first calls Fibonacci of 3 as well as Fibonacci of 4 and Fibonacci of 3. Fibonacci of 4 will further call its lower two numbers. This keeps on executing until we reach the base case. And here we have taken three base cases. When value is 0 or 1 or 2, we are just stopping the recursion and just returning the value. Okay, so let's move on to the identification of recursive problems. This is how we identify recursive problems. There are two kinds of problems which can be solved using recursion. I just classified these problems into two types. I mean, this is how we can identify a recursive problem. If we are given a problem, then we just need a way in which we can identify that this problem can be solved using recursion, right? So these are the two ways we can identify it. If a problem is involving choices and we have to make some decisions, then there comes the recursion into action. We can use recursion and solve that problem very easily. So whenever there are choices and some decisions are to be made in that problem, we can easily use the concept of recursion and we can form a recursive tree. I'll explain very clearly. Let us take some problems in both of these methods and just see how recursion is used to solve such problems. And one more type of recursive problems are working on the smaller input. So I think you might have guessed that this Fibonacci is of type 2 and you might have already studied the factorial program using recursion. In that, what do? We will just see factorial of n. What does this do? This will just make n into
factorial of n minus 1, right? This will just make a recursive call on n minus 1, n into n minus 1. This will be a recursive call. What is this doing? See, suppose if the value of n is 5, we are just calculating 5 into 4 factorial. It means when we are given a value, we are just working on its smaller input. We are just reducing the input by some value and calculating the answer for this smaller input. And from that value, we are calculating the answer to original problem. We are just multiplying it by 5 to get the answer for the original problem. This is what smaller input problem means. Okay. So now let's look at some smaller input problems. And the first one which we are going to take is decimal to binary conversion. I hope every one of you is aware of decimal to binary conversion very well. Suppose we are given a value 10. You need to convert it into binary. What do? We keep on dividing it and take the reminders. And here when we get a 1, we will just stop because uh, dividing 1 by 2 will also be giving the same. And at last we will take all this in the reverse order, right? This is what is the method to convert a decimal number into binary. So how can we use the concept of recursion over here? See, here we need all of these in the reverse order. This is where you need to get the idea of recursion. We can see what we have to do is first we need to calculate the remainder of the smaller input, and then the remainder of the original problem has to be added to the string. Actually, we need to find a binary string here. We are given an integer x, and binary string should be returned, which will be the corresponding binary representation of that decimal number. And the base case over here will be when we are stopping the recursion. Whenever we get a 1, we will stop the recursion. So if x is 1, or even if it is 0 also, suppose if 0 is given, what do? If the value is given to be 0, then answer itself will be 0. Corresponding binary string will be 0. So to can, and in this case, as well as the other cases when we get 1 here, we are just writing x less than or equal to 1. If x is less than or equal to 1, just append that value to the string character of x. What is this? I'm just typecasting to char type because string doesn't allow an integer type value, right? And x is actually an int type variable. How can you store int type variable in a string? It's not possible. So before appending, see what does appending mean? In the STL part, you have learned that append just means to add a character at the end of the string. So to do that, we will use this plus sign that is called append sign. S plus is equal to, so I think you know this notation in C programming also. A plus is equal to 2. What does that mean? A is equal to A plus 2. That is what I'm doing. S is equal to S plus char of X. So if X is 1, 1 will be appended. X is 0, 0 will be appended to this. Okay. So we are just making a call on the smaller input. See here, here the reminder is 0. So what we are doing is we will call the same function decimal to binary conversion des to binary on the smaller input, which is x by 2. We have taken input as x, so it's x by 2. What does this do? This will calculate the binary string of 5. And what you need to do? You just need to append 0 at the end of that binary string, isn't it? So what will be the binary representation of 5? It's 1, 0, 1. And if you add 0 at the end, this is the binary representation of 10. Got it? So what we have to do is, whenever we are given an input like x, we will just make a recursive call on x by 2. What does that do? It will find the binary string corresponding to that number. So you just need to append the reminder in this case. Okay. But what it happens internally is that this 5 again makes a recursive call on 5 by 2. Right? And this 5 by 2, what is it? It's 2. So 2 by 2. Again, it makes a recursive call. 2 again makes a recursive call. 2 by 2. Okay. And here we get a value 1. So 1 will be returned back. Here we get a value of, here the reminder will be 0, right? See, 10 is the initial case. Now 10 makes a recursive call 10 by 2. This is the case where we get 5. Here we get value to be 2, and 2 further makes a recursive call of 2 by 2. Here we finally get a reminder of 1 because 1 will be left out, and here the reminder will be 0. So 1, we will append the 0 from this, and here the reminder will be 1, right? 5 divided by 2. When we divide that, we will get a reminder of 1. And here the reminder will be 0. 1, 0, 1, 0. Is this fine? Let me explain you the recursive stack also. See, initially function call is made on Fibonacci, sorry, decimal to binary, just assuming it to be a small function f, decimal to binary of 10. Then we will just make a function call on 5. Then 5 will further make a function call on 2 because 5 by 2 will be 2. And then f of 1, 2 by 2 will be 1, right? So here we will just, here the string will be empty. Here we did not append anything into the string. We were just making the recursive calls. Here the string will be empty. So first we will append a value of 1 to the string. Okay. Then when the call, when the recursive function will be returning a value 1 and this will be continuing its execution, then here what do? We will just append a value of reminder. So what is 2 modulus 2? Modulus operator, I think you all know. It is just to find the reminder. So what is it? 2 modulus 2. It will be 0. So append 0 to the string. Now this will be called returning its execution to f of 5. So f of 5, what does that do? It will calculate the reminder. Right? 5 modulus 2. What is it? It's 1. So append 1 to the string. Then finally execution is returned back to the parent, that is 10, and this will also calculate its reminder, and that will be 0. So this is what will be the result, and this is the final answer of representation of 10 in binary format. I hope you understood the problem. So let's move on to the next problem. This is a very famous problem called Tower of Hanoi, and let me explain you what happens in this Tower of Hanoi problem. Tower of Hanoi, we will be given 3 stacks. Let us name these like A, B, C. And then what we have to do is, we will be given some plates, like you can consider them as plates or piles, blocks, whatever. So you will be given some blocks, and those will be of different sizes, and they will be arranged like the largest will be at the bottom and the smallest will be on the top. This is how they will be arranged. And our target is to transfer all of these into a destination stack. So these are you can call these three stacks, or you can call them three towers. So you need to transfer all of these blocks from tower A to tower C. Okay. And one more condition in this problem is that you can't put a smaller block on a larger block. So if this is a tower, sorry, you can't put a larger block on a smaller block. Okay. You can't put smaller one at the bottom and larger on the top. This is not allowed. Okay. So this is the problem of Tower of Hanoi. See, this image clearly shows how this Tower of Hanoi can be solved. If there are three disks given, we will transfer the first, our target is to transfer the largest one, that green disk, into the target, that is C. To do that, we will first transfer the smallest one into C, then the middle one into B, then get the smaller one back into B. Now transfer this from A to C. Okay. Then put it put the smaller one back into A and just transfer this middle one into B, C. Then at last you can transfer this smallest one also into the C. So this is how three disk Tower of Hanoi is working. So where comes the idea of recursion in this problem? In this problem, what you can do is you can just make a recursive call on the n minus one disks. Okay. So why? Because you need to transfer the largest disk from source to destination. Here our source is A and destination is C. First, you need to transfer this largest block from A to C. To do that, what you need to do? You need to get rid of these top n minus one blocks, isn't it? So what you need to do? You need to transfer these n minus one blocks into this auxiliary tower. This is just a helper tower. We are using this is just helping us to transfer this largest block from A to C. So we will just make a recursive call on n minus one, and for this n minus one blocks, the source will be A, and the helper stack, we will just take the help of C, and the destination will be B. Okay. See, I'm writing these in this format: source, auxiliary, destination. Okay. All the recursive calls will be in that format only. Then we will transfer this largest one from A to C, because now we got rid of all the smaller blocks and we are left only with the largest block in A. So we can easily transfer that from A to C, and our first task is done. Now this is what we should be repeating. We should repeat this task further, because whatever the next largest block is there, that should be transferred again to destination. So now after this recursive call is made, we got rid of all the top n minus one blocks. So what we have to do? You just print move larger block to move. You just write block in A to C. Block which is in A should be moved to C, right? You can just write source to destination, because source and destination keeps changing. You need not print A to C always. In this case, source is A and destination is C. But in the further recursive calls, source and destination will keep on changing, right? So you should not write A and C. You should write source to destination. So what we need to do next? Now we have this top n minus one in the helper stack, which is B. So you need to transfer these n minus one blocks from this helper stack to the destination. So what you have to do? You have to make a recursive call on n minus one block and for n minus one disk. And for this n minus one disk, what will be the source? Source will be the B. That is actually the helper stack of original problem, right? So for this, source will be B, and where you need to transfer all these things into C. So what is the destination? C. And we will use this A as a helper stack. It's empty now, so we can just use it as an helper stack, which will be helping or in transferring all these blocks from source to destination. So this is the code for recursive Tower of Hanoi. See, let me show you the code. Initially, Tower of Hanoi, a function will be called on n. N means it will be number of disks. Okay. So and origin, buffer, destination. These will be taken as input from the user, and we can just make a function call. Now, if n is 1, we will just move disk 1 from origin to destination. Then we will make two recursive calls on n minus 1 origin, destination, buffer. This is what I have explained. I just used the notation ABC. Here, in the code, it is mentioned origin, destination, and buffer. It's the same code which I have explained. I hope everyone understood it. So let's move on to the next problem. Now let's look at this problem. Reverse a stack using recursion. Let us see how we can reverse a stack using recursion. You have already seen what does a stack is and how it works in the first session. Stack basically works on the last in first out property, which is actually called LIFO. So whatever is the last pushed element onto the stack will be popped out first. It is just like a pile of plates. We can take the top one, not the bottom one. So see, suppose if this is the stack and it is having elements like 1, 2, 3, 4 with 4 on the top. What this problem tells us to do is that you need to reverse all these elements in the stack. So after the function call, the stack should become like this. 4 should be on the bottom and 1 must be on the top. This should happen. So for this to happen, you need to write the code and let us see how you can use recursion here. See, here what we have to do is that first take out the first element from the stack, remove this 4, and then what you have to do? You just call the recursive function on the smaller input. See, just take out one element and call the same function on the rest 3 elements. So what do you get from that function? That function will reverse the other 3 elements. See, after popping 4 from the stack, you will call the recursive function on the same stack, but with a smaller input, right? Because we have just popped out one element. So that function will return us this thing. It will return 3, 2, 1. Because that is what this reverse function is doing. What does reverse function do? We will just call reverse function on the stack after popping out the top element. First we will pop out stack dot pop. First we will pop out the topmost element and then we will call the reverse function on that stack. And what we have to do at last is that we just need to insert the popped element at the bottom, isn't it? That is the final output, right? So after this step, what we have to do is we need to insert the popped element at bottom. So now for this, we need to define another function. I'll explain you how does this function work. First, we need to pop an element x from the stack, st.top. Whatever is the topmost element, just store it in in a temporary variable x and just pop it from the stack and call the same recursive function on the smaller stack. And at last, just insert the element x into the stack. This is what we should do. By the way, when should we stop this recursion? This will be continuing its execution until a certain condition, which is actually called base condition. So in this case, what should be the base condition? We need to reverse the entire stack. We need to keep calling the same function on the smaller stack. But when we need to stop that, when we have just one element in the stack, even though we reverse it, we get the same, right? So at that case, we need not call the same function again. It is the same. Even if we call the same function, even if we go for another recursive call, it will be giving the same. You will just pop out this element, then you will get an empty stack, and then you will insert it at the bottom. So if stack dot size is 0, if it is 0 also, you need not reverse it because it's already empty. You need not do anything. It's just empty. So when stack size is 0 or 1, you can return. So this is the base condition. You need not do anything in this case. So you can just return back. So this will be the base condition. Okay. This is the code for the reverse function. If stack dot size is equal to 0, return. You can also write if stack dot size is equal to 0 or stack dot size is equal to 1. It both means the same. If then int x is equal to st dot top, it will return the topmost element on the stack. Then you are popping that element from the stack. Then you are calling the same function recursively, and finally insert at bottom. Now let's go to this function and see how that function works. So now our task is to insert an element at the bottom of the stack. Insert at bottom. Now we need to write this function. So if this is the stack and we have elements like 5, 6, 7, 8. And now if you want to insert 4 at the bottom of the stack, what you have to do? You just have to keep popping all the elements until the stack becomes empty and just insert that element. Push that element, whichever you want to insert at the bottom, and then again push all the elements which you have popped. Okay. For this, you can use recursion. How? First, pop out the topmost element. Just pop that element and just store it in a temporary variable like temp is equal to stack dot top. Use the top function to get the topmost element. Then just pop it. Then call the call the same function recursively. That is what is happening here. See, if stack dot size is 0, you need not go for recursive call again because it's already empty. You can directly push it so that the element to be inserted will be at the bottom. If stack is already empty, whatever you push will be at the bottom itself. So when will you stop? The base condition for this case is stack dot size is 0 because if stack size itself is 0, whatever you push into the stack will be at the bottom only. You need not pop other elements because there is nothing to pop. In the other cases, you need to pop the topmost element and you just need to call the same function recursively and at last you need to push it. See, this is what will happen. First, you will pop 8 and store it in a temporary variable. So temp is equal to 8 and recursive call will be made on this is recursive stack. In the recursive stack, in the first function call, there are 4 elements in the stack. Then x will this 8 will be popped out and you will call the same function on 3 elements 7, 6, 5. These 3 elements only will be present in the stack and a recursive call will be made to this function. So in the recursive stack you will get a stack with 3 elements. You will call the same function on the stack which is only having 3 elements, not 4 elements. So then what will happen? Then here temp will be 7. Temp is just a local variable to function. See, this is a separate execution of function. This is a separate execution. Here temp will be 8, here temp will be 7. We are not overwriting it. It's a local variable. It's not a global variable, right? So that is the case here. And this function will store this 7 in the temp and call the same function recursively again on the two variables. I mean, two elements. Only 6, 5 will be left in the stack. So on the 2 element stack, you are pushing it. Then you will be left with 6 and 5. Then temp will be 6 in this case. And when temp is 6, you are just left with one element. Then your stack will just contain one element. See, what is happening is here your stack contains 4 elements. In this case, your stack contains only 3 elements. In this stack, your stack contains, in this step, only 2 elements. Here, you just have one element. And in this case, you will again pop out that, again make a recursive call and store this value in the temp. Temp is equal to 5. And now we will have an empty stack. Here the stack becomes empty. You will make a recursive call after popping this 5 from the stack, right? So here stack is empty. So what do you do when stack is empty? Stack dot size is 0. Your base condition is arrived. So you just return, do nothing. You just need to return back, and this line is executed. So next, what you need to do? You just need to push that 5 into the stack. Stack dot push temp. So what is the temp in this function? It's 5. So 5 will be pushed into this. When we reach the base condition, stack dot size is equal to 0. First, we will push the element which is to be inserted at the bottom. That is 4, right? So you will push 4 into the stack. Then you will push 5 into the stack, because this condition is written right. See, first your stack contains 4 elements, and you need to push one element into this. So what you are doing is you are just calling the same function on 3 elements, then 2 elements. Then your stack just contains one element. Then finally it becomes empty. When this becomes empty, you need to push this x into the stack, because that is what our function is aiming to do. It is aiming to insert an element at the bottom. So you will push that x at the bottom, and from there you return back to this case. And in this case, we are storing whatever it is there in this position in a temporary variable. So we will push that temporary variable. Like here I have used a as a temporary variable to store the topmost element, and then I am popping it from the stack, then calling it recursively. So after that recursive call is done, when the recursive call is returned back to this pair, return back its execution to the parent, you just need to push whatever is previously existing in the stack, right? You just need to push it back. So you need to push a again into the stack. So in this case, in this case, 4 will be inserted at the bottom. Then when this function is getting a chance to for execution, it will again push back this 5, and this execution is completed. Now this will return back to the one which called this function, that is parent of this function will be this, right? This is the parent of this function. So this will continue its execution. This executed its recursive call. So what is written below a recursive call? St dot push that temp variable. So what is the temporary variable here? 6. So 6 will be pushed into the stack and this is done. So now this is returning its execution back to its parent. And what is stored in the temporary variable over here? 7. So you will push that 7 here and who is the parent of this function? This one. So again, this completed its recursive call. What is written just below the recursive kind? It's just stack dot push that temporary variable. So that temporary variable, its value is 8, so it will be pushed into the stack, and this is the output we get. We have achieved our goal, right? We need to insert 4 at the bottom, and we have inserted it. How did we insert that? You just need to pop out the top element and store it in a temporary variable and call the same function recursively on the smaller input, and at last push that element which is stored in the temporary variable back into the stack. And what will be the base condition? In the base condition, when the stack becomes empty, whatever is to be inserted at the bottom should be inserted, because if stack is empty, whatever you insert will become the bottommost element, right? So that is how you need to solve this problem. Now let's move on to the next problem, subset sum. This is a very famous problem based on recursion. And now let us see how this works. Till now, we have discussed the three problems which are based on working on smaller inputs. Now, let us see problems which are dependent on recursive trees and choices and decisions. Before moving on to this problem, one clarity which I want to give to you is that in recursion, always think about the problem like a hypothesis. Like what will you do in case of hypothesis? You used to do it like there used to be inductive hypothesis problems in mathematical induction chapter, I guess. So what you'll do is you'll just assume that this is true and you'll proceed. So this is what we should do in this case also. Like in this function, inserted bottom function, you can think of it like this. So just uh, pop out the top element, store it in a temporary variable, int t is equal to st dot top, and then just pop it out. After popping it, you just make a recursive call on the same function, insert at bottom, and on the stack which is having a size lesser than the original problem. And what you need to insert? A variable x. So what does this function do? This function will insert that x at the bottom of the stack. So your task is being done by this function. You need to assume that this will work on the smaller input, and whatever task it is given, it will be achieving that. And at last, what you need to do? You just popped out one element from the stack. You popped out the topmost element from the stack and then call this function. This function inserted x at the bottom. Your task is completed by this problem. Your task is achieved, except that you popped out one element. So what you need to do? You just push that element back, whichever you popped out. So we will just push back that topmost element, whatever you popped out from the stack. I just stored it in T, so I just wrote a condition stack dot push T. This is how you can think of a recursive problem always. This is the same approach we used in this case also, right? In reversing also, what we have done, we just popped out one element from the stack and then we call the same function recursively on the smaller stack. And what we are assuming? We are assuming that this recursive function will return us, this recursive function will give us the stack in the reverse order, but with one element lesser, right? See, actually it is 1, 2, 3, 4. If it is 1, 2, 3, 4, actually, you are just popping out this one from the top, and you are calling the same function recursively on the smaller input. So what we are assuming that this recursive function returns the value correctly, and this reverses it in this way, and this should be the output after this recursive call. So 4 should be on the top, 3 here, 2 here, and at last what you need to do? You just need to insert 1 at the bottom. Then you will be getting the correct output. That is what we assume generally. We just assume, design a hypothesis, like working on the smaller input gives us the answer correctly. That is what we generally assume in recursive problems. So that is why I named this kind of problems as smaller input problems. And okay, now let's move on to this type of problems where we have some choices and we have to make some decisions based on those choices. And in these cases also, let's look at two problems so that you'll gain some knowledge about these kind of problems. So first of these two will be subset sum problem. And what this problem is actually is, we will be given a list of integers, like we will be given with an array, and you need to return the sum of all subsets in the increasing orders. See, from every array you can make some subsets. Like if you are given some elements like 1, 2, 3, 4, 5, how many subsets you can make? I think you know that it is for 5 elements you can make 2 power 5 subsets, right? So you can take just one element subsets, 1, 2, 3, 4, 5. We get 5 such one element subsets. Similarly, if you consider two element subsets, you get 1, 2, 1, 3, 1, 4, 1, 5, like that. So in this case, what we are having is, see, I'll explain from this diagram itself. If our array is having three elements like 3, 2, 1, here we have a choice. What is that? We can consider an element. We can pick that element into our subset, or you can just neglect that element into our subject. You can just leave that element out. So for every element, we will have two choices, either to pick that element or to leave that element. So for starting from the zeroth index, like the first element is 3 here. So first you just pick the 3. Then what will be the sum? Sum will become 3. In this case, you just leave that 3. Sum will be 0. Then you'll move to the next index, because for 3 we have explored both the choices. Now just increment the index. So index will become 1. Now what will be array of 1? That is 2. So if you pick the 2, then the sum will become 3 plus 2. If you don't pick it, sum will be 3. And here also we have two choices for 2. You can pick it or you can skip it. If you pick it, sum will be 2. If you skip it, sum will become 0. Sum will be remaining as 0. So in this case, again, you have two choices for 1. At each level, we will increment the index. Like we are getting a tree here, right? This is actually called recursive tree. This is the recursive tree, right? We have already seen what recursive tree is actually. Here we are just drawing a recursive tree based on the choices and decisions we are making. So at last, we can just consider this one also, and then the sum will become 7. If you neglect 1, the sum will remain as 2. In this case, we have two choices for 1 again, pick or not pick. In this case, similarly, in this case. So 3, 2, 1, we are considering all the three elements. In this case, you are getting a sum of 7. In this case, we are considering only 3 into the into the subset. So this is a one element subset, and this is a three element subset. And what is this? It's a two element subset. It's a one element subset only. Just three is taken. Here it's a two element one. It's a one element. It's just having one element, and it's a null set, empty subset. We are not taking any elements. That is also a subset, right? Every null set is also a subset. So this is the, so this is how you can find all the subsets. and we have already calculated the sum of all the subsets. What you just need to do is you need to return all these sums in an increasing order. What you can do is you can just push all these sums into a vector. So you already know what does a vector means. It's just a array. It's just a simple container which is very similar to array, except its dynamic nature. That is the advantage of vector over arrays. So at last you can just sort the vector, and for sorting the vector you can use this v dot begin comma v dot end. Always we need to pass the starting and the end pointers to the sort function. That is why we are passing this v dot begin. V dot begin returns the pointer to the first element of the vector, and v dot end is the pointer to the last element of the vector. So we need to pass both the first and the last pointers to the sort function so that it will sort the entire array and will return us the output. So now let's look at the code once. This is the main function and we are just declaring an array, and we will just make a function call to that subset sum function, and we are passing a vector as well as the size of the vector to the subset sum function, and we are declaring a vector int as which is our answer. We just need to store all the sums in a vector, right? So for that we are just declaring an answer vector, and then we are using a helper function to do that, because we need to store the index of the current element, like index which starts from 0. So in the first call it will start from 0. That is why we are storing we need to store index, because we just need to know till how many levels we have traversed. So to do that we just need an index, and we need array, size of array, and the answer vector. Answer vector, see here you need to notice that we are passing it by reference, so that whatever we add into this vector will be reflected over here also. Okay, and we also need an variable sum, because we need to store the sum also. At each level sum will be changing, right? So to do that we need a sum variable also to be passed as a argument. So for this function, what will be the base condition? When we reach the end of the array, like in this case, when we reach the end, 3, 1, 2, when we explore both the choices for 2, we will just increment the index in the next call. So when you increment this, the index will go out of array. So here you need to stop, because you don't have any other choices to be explored. You have already explored all the choices. You have already traversed the entire array. So you covered every case. You need not continue recursion there. So you just push whatever the sum you got into the answer vector and return back. Okay. So this is the base condition, and then this is the first choice. If element is picked, then what you need to do? If element is picked, we will just go and explore the next one, next index. So we are incrementing the index. Okay, let me clear this. Okay, so in each case we will be incrementing the index and just pass the same vector, and size will not change. Answer vector we will just pass it, so that we will push everything into the answer vector. And when element is picked, what about sum? If you are picking that element, then what does that mean? You need to add that element into the sum also. So in the recursive call, you will just add that element to the sum. So array of that index, whatever index is that, you need to add that element to the sum, and in the recursive call you need to push this new sum. You need to call the recursive function with this new sum, because this is the current sum. in this case. And in case if the element is not picked, what you need to do? If element is not picked, that index is done. So in the next call, you will go for the next index, same ARR and N, and answer doesn't change. And in this case, element is not picked, so sum doesn't change. Sum will be the same which was previously there with that function. Whatever was the sum in the previous, it's in its parent, that will be the same sum because we skipped that element. We did not pick that element. Okay. So I hope you understood this question. So now let's move on to the next question. This is this is also a very good problem. This can be solved more easily using backtracking, but I have taken this problem to show the use of backtracking. Like you should also know in what cases backtracking will be easier than recursion. Backtracking, we will discuss it very soon. So before that, you just try to solve this question using recursion first. Then we will know how this can be solved easier, more easily using that backtracking technique. So the question is asking us to print all the permutations of a string in the lexicographical order. And lexicographical just means that you need to print all of them in the sorted order, like how it will be there in a dictionary. Here, what you have to do is, suppose if we are given a string like A, B, C, D, what you have to do is that in every case, we will have two options. Like you can just see, if I take 5 elements, the recursive tree becomes very big. So let's just take 3 elements and just continue. If I have 3 characters in a string, if it's 3 character string, A, B, C, then how can you get all the permutations? See, in case of permutations, what choices you have? See, our output string should contain 3 characters, and for each of the character, you have 3 choices. First character, we have 3 choices. What are the choices available for the first character? You can select any of the 3 characters available in the string. See, for the first character in our output, we have 3 choices because we can use any of the 3 characters. And for the second character, whatever we have already used, we will just neglect that character and we can use the rest 2 characters. And for this, we have 1 choice. So in this case, our recursive tree will look like this. For the first case, we have 3 choices. Now, suppose if we have considered A to be the first character, we will just be left with BC in the input and A will be the output. This is output, this is input. Okay. So in the second case, our output is having B and input will be left with AC. This is the output, this is the input. In the third case, we will be taking C into the input. So, sorry, C into the output, input will contain both A, B. And this is the first level of recursion tree. And what will happen in the second level? Now each of these just have two choices because now we just have 2 elements in the input, right? We are not having 3 elements, so we don't have 3 choices. We will be just left with 2 choices. So we will just suppose if we consider B into the output, A, B will be the output, and we will be left with C. And here B, A will be the output, we will be left with C. So if we consider C, AC will be the output, we will be left with B. Here, if we consider A, we will be left with C, and if we consider C, we will be left with A, and output will be BC. This is the output, and this is the input here. Okay. So in this case, CA will be the output, CB will be the input, and corresponding inputs will be BA because that will be the character left out. Now we don't have any other choices because we are just left with one character. And in a permutation, number of characters in the input should be number of it should be equal, right? So you can't skip a character. So when the input size is one, you just don't have any other choice. You just need to push that element into the output. You just need to append that at the bottom. I mean at the last. BCA and here CAB, here CBA. So these are all the permutations. These are the only possible permutations we can get. So for a three character string, how many permutations we can have? Two cube only. Na? So we have got all the eight permutations. I just did not take the example of five character string because I can't represent 32 different strings in this page. So just took a smaller example. Hope you understood the problem. So in this case, what we have to do, we will just pick one of the character, one of the three characters, whatever is the size of the array, one among them will be taken into the output and rest characters. I mean, whatever the left out characters that will still remain in the input, and we will just uh, move to the next index then, and there whatever will be the characters in the input, we will have that many choices in each level. In each level, we will be having number of choices is equal to number of characters in the input string, isn't it? Here we have three characters in the input string, so we got three choices. In the second level, we just have two characters, so we have two choices. And when the number of characters becomes one, we are not left with any choices. We just have to take that character. We are just left with one choice. So if we are just left with one choice, it doesn't mean by making any decision. There you need not make any decision. You just need to include whatever is left. So that can be taken as the base condition here, right? What is base condition? Whenever we need to stop, that should be taken as the base condition. Or you can just take a zero size string as the base condition, or you can stop when when input size becomes one, because when input size becomes one also you need not do anything. You just need to append that into the string. So what you can write here is, instead of this condition, you can also write this thing. If input size, just keep that condition like that, because then only it will handle the case. If input size is 0, then your code should work now. So for that, this condition should also be there, and for along with this condition you can also add this condition. If input dot size is equal to 1, just append the current character. Op output plus is equal to the character which is left in the string input of 0, because we only are left with one character, so that will be available at the 0th index. You can do this, and after that you just push back that output into the vector. We are storing all the output strings in a vector. See, we declared a vector of string. Vector of string, what does that mean? It will be storing various strings. Like, see, here we got different permutations, A, B, C, B, A, C. It will store all these permutations in a vector, and finally we will return that vector of string. This you can do. This base condition can also be added. You can also write this thing as a base condition. Now let's look at the code clearly. We are using this solve function in order to do these recursive calls. And for this solve function, what do we need? We need the vectors vector of string v, because in this you need to push that permutations final, the result should be stored in this vector. So we are passing this by reference. Basically, this means to pass by reference. In the C programming, you have seen that you will pass address of something. Like if you pass like this, you will just declare a pointer in the function. In this function, you will declare a pointer in case of C programming. But in case of C++, you can directly mention and here, which means passing by reference. And here you need not mention and. This is the opposite case, right? In case of C programming, what we usually do, here we will write and v, and here you can write, you can declare a pointer. But here we don't do that. Here you just need to mention the name, and here you just use this and operator. This means you are passing that by reference. I think you understood the difference here. This is the difference in C and C++, one of the difference. So this is the base condition. I have already explained you base condition, and also you can use another function which I have already told you. And these are the choices we have. What are the choices we have? We need to travel on the input string, because whatever is the input string size, that will be the number of choices we have. So for each character on the input string, what you will do? You will just add that character into the output. See, if you are having a string like A, B, C, D, if you are at this index, suppose if I is equal to 1, what you will do? You will take B into the output. So you just append out B to the output. So output plus S of I. We are just storing it into a new output. We are creating two new strings, new input and new output, and storing that out. It stores the value output plus the current character S of I. And what will be the new input? In the new input, we have already taken this character, so we are just left with these three characters. So you need to remove this character. For doing that, you can use an erase function like s dot erase of. You need to return iterator to this position. So what you can do is you can write s dot begin plus I. Okay, because s dot begin will be iterator to the starting position plus I, means whatever is the index of that particular character, that will be the that will be added to this pointer. So see, in case of C programming, you might have seen like this. If you add 1 to the pointer, it will point to the second element. See, currently if see, let's take an array like 1 2 3, and this array is named as A. So what does A mean? Pointer to the first element. And if you take this star of A plus 1, what will be the output? 2. Why? Because when you are adding 1, it means that you are adding whatever is the size of that particular data type, you are adding that to that pointer address. So this will move to second position. So here also you are doing the same. You can do this s dot begin gives the iterator to the first position, and to that you are adding this index I. So that will give this index, this point. We will get an iterator pointing to this position. So you can erase it in this way, or what you can do is, let me clear this. Or you what you can do is you can just make a substring. This is substring function. See, I am telling another way to write this line, that is by using an arrays function. That is just what we have discussed. And instead of using arrays function, you can also write it like this. Whatever is written in this code, what you can do is, whatever will be the input, just take the substring from 0 to that index and I plus 1. See, this function will take all the characters from 0 to I, but in case of I, it will be an open bracket. It will include 0, but it will not include I. This is the how sub-str function works. Sub-str function, what it actually means is this will be the starting position and this will be the length. So from 0th index, it will count I characters. So it will not include the ith character. So in case of ith character, it should be an open bracket. So we will be leaving that ith character and again input dot substr I plus 1. This means if you are just giving one parameter to substr function, what it means is it will take all the characters from that position till the end of the string. So if you are taking from I plus 1, it means from I plus 1 to n. So n is the size of the string. Okay. So what you are doing from 0 to I minus 1, you are taking every character, leaving the ith character, and from I plus 1th character, you are again taking every character till the end of the string. So you will get the string completely excluding the ith character. So this is how this substr function is used to achieve this thing. Or you can also use the erase function like how I told, and then call the same function recursively on the new input, new output, and the vector of string which is given. Okay. Whatever are the parameters needed for solving that recursive function, we will use it. See, in this case, what are the parameters we are using? We want to know the current index also. We want to know the current index, we want to know the sum, and we need this array, right? These are the parameters we need, and we also need one answer vector to store the answer, right? To store all the sums, we need to return all the sums of different subsets. So to do that, we need a answer vector. We need this original input string, which input vector which is given, and we need a sum variable, as well as we need index of the current position. So here we have included all of them in our code. Index, given vector, the size of the given vector, answer, as well as sum. This size you can skip because you can also use arr dot size. Size function can be used. Similarly, in this case, we just need input, output, and the answer. Here we don't need the current index because whatever will be the size of input on each of these characters, we will iterate. So we don't need the index especially because we are already having the input string as a parameter. We don't need index. That is why we are using a for loop here. We will traverse on each and every character in the input string. So that is how you can solve these kind of problems. Now let's move on to next concept, backtracking. Backtracking is nothing but it's just recursion with just one extra line of code. Except one extra line of code, you don't have anything in backtracking. And that last step is called backtrack. And what we will do is we will try all the different paths. And when you hit a dead end, it means if this choice is not needed, then what you will do is you will just backtrack. Backtrack means you will just go back to the previous case. You will not continue the recursive call further in that case because that is not the case which you need. If you find any such case, you will just backtrack to the previous case. That is all about backtracking. It's nothing just but recursion with one line of one additional work. It may be one line or maybe two lines, whatever it is. One step. It's just additionally what we have to do here is you just need to do one additional step, which is actually called backtracking. And to identify backtracking, see, I forgot to discuss time complexity in these cases. What will be the time complexity in these cases? See, in case of subset sum, you have 2 power n different cases. So you have 2 power n recursive calls you will be getting, right? I mean, all the calls together will be 2 power that input size. So that will be the time complexity here. Recursion always has exponential time complexity. And what does exponential mean? Exponential means in powers, like you'll get time complexity in these formats, like 2 power n, 3 power n, some number power n. This is called exponential. So for recursive problems, time complexity will be exponential. So how can you identify that? See, whenever you are solving a problem, say on CodeChef or Code Forces on Lead Code, you will have constraints written over there, like input size. If input size is something like this, to 15 or 16, something like this indicates that constraints are very small. So in these cases, like 2 power 15, it's acceptable. But if you say size of n is like 10 power 5, 2 power 10 power 5, is this an acceptable time complexity? If your program takes this much time, can that be executed? Never, right? So you can identify these recursive and backtracking problems using constraints also, because generally the time complexity in these cases will be exponential. So constraints should be less. And I have already told you two more methods. How can you identify those recursive problems? If you can solve it by taking smaller input, then it means definitely need to use recursion in that problem. And one more thing is, in case you have some choices and decisions to be made, you can use recursion to explore all the different cases. So now let's come to the same problem. We already did the same problem using recursion, and now let's do this problem using backtracking. Let us just see how you can solve the same problem using backtracking. What we are actually doing in this case is that we are just uh, taking one of the character into the output and remove that character from the input and proceed. So instead of doing that, what you can do simply is to permutation just means that you are interchanging characters among themselves, isn't it? So what you can do, you can just swap the characters among themselves instead of making new strings. See, the complexity, this is increasing the time complexity. The procedure which we have done using recursion is increasing time complexity, because you might have know you might have known the thing that substr function, substring function takes linear time. Linear in the sense, whatever will be the size of the input, that much time. We go of n time it will be taking. Isn't it complex? I mean, it is increasing the time complexity, right? Can't you do it in lesser time? If you are using something like a swap, because it's just about interchanging characters. So why can't you just swap? Swap, you can just swap two characters, and swapping just takes linear constant time o of one time. So this is decreasing the time complexity, right? In every case you are taking a linear time because of substr function. Isn't this increasing the time complexity of whole program? It will increase, right? It will affect the execution time. So to reduce the time complexity of the function, you can use this function. You can swap two characters in the same input string, and you need not even create a new string or output, because you can just swap characters in the input and just push it into the answer. That is what you do in this case. You can do that. I'll explain why. I'll clearly explain you what is backtracking. See, this last step is called backtracking. I'll explain you why it is actually called backtracking and what it actually does. Everything will go clearly. Now, see, this is the main function. The string is given, and we are just calling a function permute on that string, and the zeroth index and the last index are passed to the function. ALR. What will be the base case? When the starting index reaches the last. See, let us see how this problem can be solved using this backtracking technique. I already told you backtracking is nothing but recursion. So we will just try to make recursive tree for this question using this swapping technique. Instead of just using that substring function and splitting the string into two, we will just swap the characters in the original string itself. Okay, because that will reduce the time complexity, right? So what are the choices we have? See, in this case, we will start with the zeroth index. So what we will do is we will start for each index. What we will do is we will try to swap both characters. Like we will maintain two pointers. Like one will be pointing to the see. Let's take like I and J. Okay. Initially J will be 0, then J will be 1, then J will be 2. Okay. So let's compare, let's swap these I and J always. So see, initially Ij will be pointing to the same element, so you'll not get anything difference. You'll be getting the same string. You'll not get any different string. And when J moves here, I will still be there. So you can swap these two characters. Ij will be swapped. So BAC. This will be one of the permutation you will be getting. Then if you swap these two, first and the last, what you are doing is actually start with one index and swap it with every other index. Okay, every other index which is higher than the current index. Okay, then you will swap C, B, A. This will be the output, right? When you swap A and C, this will be the output. So at this level, you are done with first index. You have already swapped first index with every other index. Now move to the second index. Okay, this is done. Now everywhere you are at the second index. So second index, what are the choices you are having? Just swap that index with itself. So you will not get any difference. So it will remain the same. ABC, swap it with the next index. So ACD. This is one of the output you will be getting. Here first will be same because in the first decision we will not swap it with any other character. We will just swap it with itself. So you will not get any new string. You will get the same. In this case, you will swap these two, so you will be getting DCA. Here, it's CBA and CAB. These are the permutations. So now your index variable points to the last character. And here, what are the choices you will have? You can just swap it with itself because after that index, you don't have any other indices because that's the last index. So when you are reaching the last position of the string, like if our index, if index idx, let's say if you are storing index in idx variable, if index is equal to let's say if you are given an input yes, if it is yes dot size minus 1, isn't it? What will be the last index of a string? S dot size minus 1, because S dot size gives 1 plus, because counting starts from 1, right? In case of length, you will calculate length from 1. See, what will be the size in this case? If you use S dot size, it will return 3. But what is the index of this? It's 0, 1, 2. So that's why I have written size dot minus S dot size minus 1. So if index is equal to S dot size minus 1, you are done with all the permutations. This is one of the permutation. You got one of the permutation. So you just push it into your answer vector. ANS dot push back that string, whatever is that string. Like if it is V, just answer dot push back V. Or if it is yes, whatever it is, whatever you can name it anyway. So this is what we are doing in this case. This is the recursive tree diagram of the permutations problem using this swapping. Isn't it the same? It is exactly the same. But what we are doing here is we are additionally creating new strings. We are just splitting the original string into two. Instead of doing that, what I have done here is I have just swapped characters among itself in the input. Okay. And one more thing is that, see, if I am swapping these two characters, first I'll get this. Then in the next recursive call, I'll get this. Then ACB, I'll get this. So from this, when this recursive call is done, this will be returning back. When this recursive call is done, because we are reaching the last index, right? So we will just push this ACB and we will revert back. We will return back to this ABC. But we are passing the input string by reference, right? So if we are passing the input string by reference, whatever the change we are doing here, that should be, that will be reflected in this also. So here, this will no longer remain ABC. This will also be changing back to ACB, right? Because this leaf node is having ACB, this changes these two characters, and in these calls, we are always passing the string by reference. So the parent string should be ABC, but as the child recursive call made it ACB, the parent string also will be having ACB because it's a path by reference. So it's like a global variable. It will be changed everywhere. The change will be reverted everywhere. It will be reflected there also in the parent also. So here it will no longer remain ABC. It will also be changed into ACB. So what you need to do is you need to backtrack. This is the change you have made, right? From ABC, what change you have made? You swapped these two characters. So again, you swap these two characters. After swapping these two characters, it became ACB. So while returning back to the parent, after this recursive call is done, now you got the output. This output is fine. Now you need to explore other cases. In order to explore other cases, your input string should not be changed. Your input string should be same as the given input. Given input is ABC. But after first recursive call is done, your input string is being changed to ACB. This should not happen because your input string should remain as ABC. So to achieve that, what we are doing is we will swap these two characters again. After the recursive call, we will swap these two characters again. So you can swap it like I have assumed ij two in this two pointers, right? Two. So you just swap s of swap of s of I and s of j. You just swap s of I and s of j, and that will be done. Before returning back to the parent, you just need to swap these two things. That is what I want to tell. And this step itself is called backtracking because here we are just reverting our changes back. We are just uh, what can I tell? Uh, just going back to the previous state. We are just modifying it back to the previous. So this is actually called backtracking, and that is what we do. See, in this case, what are the parameters we need? This input string is needed, right? Let us assume that to be yes, input string is needed, and we also need the current index I, and we also need one vector for storing our answer. Here he just directly printed out the output, so he is not using any vector. So you can also do this if you are asked to print the permutations, you can directly write cout because cout is the function used in the C++ to print things similar to printf in C. You can do this, or if you are asked to return the permutations in a vector, you can just push back into that vector. This is the base case if uh, index reaches the end of the string. I mean, it will be equal to s dot size minus 1. You can just push back the v dot push back that size, that string, push back that string, and just you can return. In other cases, what you have to do is you just swap these two characters, swap. You need to traverse from all the indices next to it, like declare a variable j int j is equal to I2, j less than n comma j plus plus. I will be the current index. We need an parameter I, we need a parameter s, and we need a parameter v. This will be storing the answer. This will give us the current index, and this is the given input stream. These are the parameters, and I'm just defining a solve function to solve the problem. This will be the code. This will be the base condition. If s dot size is equal to 1, just push back that string into the vector and just return. In all other cases, we will need to explore all the cases from that particular index to all the next indices, right? From j is equal to I2, j less than n, j plus plus. Keep traversing from I2, all the indices in the string, and just swap s of I and s of j. And after swapping, just make a recursive call on the just say call the same function, but now this index is currently explored, so you just need to increment the index and pass the same string yes. And what you need to do, what will be the other parameter, pass the same vector. And after this, what is the step which we have discussed? We just need to do backtracking, because we have modified the given input stream. When we need to go back to the parent case, we need the original string. So to do that, we will swap s of I and s of j again. So to understand this better, I recommend every one of you to dry run the code once. Dry run just means you just take a sample input, like you just take a case when input is ABC and just try how this code is working on that input. Just work out the this take an example and just run that code. You just manually run that code. I think you understood the problem, but once again, I'll just go briefly on this backtracking step because this is very, very important. See, first we are just swapping A with itself. Then we will get this ABC. Then we will swap A with itself, ABC. And this A will be swapped with the first index character, that is B. And that will become, oh, sorry, current index will be this, right? So B will be swapped with C, A, C, B we will be getting. And from here, when we finish executing this statement, we will just uh, swap these two characters again in order to get the original string, which is ABC. And after execution of this, we will again swap this with itself. The current index is here is this, right? See, how did we get this ABC? By swapping A with A. So when we are going back from here to here, we need to swap A with A again. Here it's not changing, so you might not get any difference. See, but here you can clearly notice the difference. Here you can swap A and B first. From that you will get this BAC. then BAC will remain the same, and then BCA you will be getting. So from here, when you are returning back, you change it back to BAC. Okay. And from here, when you are going back, this input is changed now. This input is BAC currently. So here also the input will no longer remain ABC. It will become BAC. But you swap these two characters initially. So again you swap these two characters to revert to the original string ABC. This should be ABC, but due to this function call, it will become BAC. Okay. So we are just swapping those two characters again. That is actually what we call backtracking. And this is what backtracking is all about. I hope you understood. And now let's look at a follow-up. If duplicates are present in the input, what if duplicates are present in the input? What can we do in this case? See, if input string is having duplicates, then what we should do? If duplicates are present in the input, what we should do? In that case, see, suppose if the input string is like this, and in this case, if you swap the first one with itself, we will get AABC. If you swap this with the first character, you will get the same AABC. And if you swap it with this, then you will get BAAC. And if you swap these two, then you will be getting CABA, right? And you will continue the recursive calls with these two. All the outputs in these two cases will be the same. So what you have to do is whenever you get a duplicate, if uh, its previous character is already traversed. So see, like if here we have already executed it once, then you can skip this recursive call. You need not do this because all this will be the same as the first case. Whatever the outputs you'll be getting here, that will be getting here. So why should we do this unnecessarily? So here, what we can do is you can just use an set. Let me show you how can you modify the code there. You will just write the first base condition, and just after the base condition, before the for loop, just declare an unordered map in the main function itself, and it will be empty initially. So unordered map, or you can use set. Suppose if you declared set with name set, you just use this thing. You use this line for in the for loop. For of int something like I is equal to index idx comma I less than n comma I plus plus. What you can do is before going for the recursive calls, before doing the swapping, you can just check it in the whether it is already present in the set or not. If it is already present in the set, what does that mean? It means that it is arriving for the second time. It means it's a duplicate character, so we need not proceed for the recursive calls. So do this thing, like use this condition before doing the recursive calls and swapping them. And if set dot find of s of I is equal to set dot n, then you can proceed for the swapping and then recursive call, then followed by backtracking. And after this, you insert the element into the set. Set dot insert whatever the character it is, insert it into the set. This is how you can solve this question. And to solve this second follow-up, return permutations in lexicographical order, what you can do is you can sort the final output vector string, or one more thing which you can do is to sort the initial input itself, and then you can proceed for the recursive calls. In case if the input itself is already sorted, then all the outputs you will be getting will be in the sorted order. Because see, if it is like this, then you'll be getting something like A, B, C. A will be at the start, right? This and for the last recursive tree, I mean last child, there you will be getting C in the start. So this will be in the sorted order, isn't it? So to get all these in the lexicographical order, what we can do is we can proceed with the normal given input, and finally after storing all the things in the final answer vector, you can sort that vector, or else what you can do is you can sort the input string itself and proceed for the recursive calls. In this case, you need not sort the final vector because outputs will be already sorted. So this is how you will be achieving the second follow-up question. So let's move on to the next question. Letter combinations of a phone number. This is a very easy problem which I have taken from Lead code. See, this is the question. In this question, we will be given with a string like digits 2, 3. Digits. A string will be given with name digits. It will be having numbers from 2 to 9, and we need to return all possible letter combinations that the number could represent. See, in a telephone, what does this 2, 3 can represent? 2 denotes A, B, C, and 3 denotes D, E, F. So what can be the combinations possible? What are the all? See, we need to return all the possible combinations: A, D, A, E, A, F, B, D, B, E, B, F. Similarly, with C. So this is how you need to solve this question. And if it is empty, we will just return an empty vector. So now let us see how can you solve this question using this backtracking technique. This is the same question. We will just map each of the first, I mean, see, in each of the cases, if it is like if it is 2, 3, then 2 can be, 2 has this mapping, and for 3, mapping will be DEF, right? So you have two choices available. So you can select one of these three and you can select one of these three. You need to make decisions. So this is where the idea of recursion comes. Choices and decisions are there. So you can use recursion to solve this problem. And we are using pass by reference. By the way, I forgot to discuss one thing. By now, you must be getting a doubt that why should we even do pass by reference? Because of this pass by reference, we are unnecessarily making a backtracking step. If there is no pass by reference, we need not backtrack because that variable will be local to that function, right? If there is no pass by reference, we need not even backtrack. But still, why are we using this pass by reference? It is because pass by reference doesn't create copy of own function. If we are using it, if we are just passing it by value, then every recursive function call will generate a new variable, right? This will increase the space complexity of the program. So we are just reducing the space complexity by passing it by reference. And this will also affect the time complexity. It will not affect the time complexity, but it will affect the execution time of the program, actual execution time. Time complexity is not the actual execution time, right? There are many other factors like memory, everything. You'll get to know all these things soon. So yeah, now let's proceed to this question. So in this, we need to return a vector of string. So we are declaring a vector of string. And if digits dot length is equal to 0, just return that empty vector. And we are creating a mapping for 0. There is no characters. For 1, there are no characters. For 2, ABC, 3, 4, similarly up to 9. Then we will call a function solve. And what are the parameters we needed? We will just need that answer vector, digits string which is given, index, and also this mapping. Along with this, we need a string to store our answer, right? We need to store that combination, right? To store that combination, we are using a string called result, and we are initializing it with an empty string. An empty string initially. And what will be the base case? See, as long as we have digits, we have choices. So when we reach the end of digits, if we have just two in the input string, like string digits, if it is just two numbers, then whenever we reach the end of this string, like 0, 1, 2, if we reach the index 2, there is nothing over here. So you can just stop it here, stop the process here, stop the recursive call, and just push whatever is in this result string into the answer. So that is what we are doing in the base condition. If I is greater than or equal to digits dot length, we will just push back the result into the answer vector. And in the other case, if it is digits, if it is not the base case, then what we should do? See, if it is two, this is in the character form, right? This is a string. So what we are doing is digits of 5, 2 minus 0. Character 2 minus 0. This means this will return value 2. It is a character. That is why we are subtracting 0 from it. Because this will have an ASCII value. See, here we need to subtract it by ASCII codes. So what will be the difference between ASCII code of 0 and ASCII code of 2? It's 2, right? So to get 2, we are subtracting this digits of I from 0, because digits of I is a character. You can't store it in an integer variable. How can you store a character in an int variable? Okay, so next, proceeding further, then what we have is for int j is equal to 0, j less than value dot length, j plus plus result dot pushback value of j. So see, this whatever is the current index, like if it is 2, then our string val will be a b c. So what are the choices we have? Whatever is the size of this value, that many choices we are having. So we are iterating on that string value. Okay, so for each of these we will just push that character. See, first see, you have three choices over here. If it is 2, you have three choices: A, B, C. You can push any of these. Then for 3, again you have three more choices. What you can do? AD, AE, and AF. Similarly with B, you have three more choices. Similarly with C, you have three more choices. This is how recursive tree of this problem looks like. And see, we found the value at that place by subtracting it from 0. That will be ASCII code. See, character 2 minus character 0. This will return a value 2, right? So from that, we will get this string val from the mapping. We have already defined this mapping here. And then we will just push that into the result vector, result string, and then proceed for a recursive call. You just need to do recursive call on that result, answer, digits, and now increment the index, because you have already processed this thing. This index is done. Here you have taken the decision already. So this decision is yet to be taken. So you just need to increment the index and do a recursive call. And at last you need to pop back from the string. Why do we need to do this? This is what is backtracking actually, right? See, because you are actually pushing A into the string. What are the choices we have here? A, B, C, right? So initially we have an empty string. From empty string, first we are pushing A into that. So after this recursive call is done, when we are returning back, now we again need an empty string. How can we get that? By popping back whatever we have pushed. So we need to result. we need to do this step, result dot pop back, because here it is A. In the next case, in the next iteration, now for J will be incremented. When J is incremented, you need to push B into the string. So A should not be there, right? Our choice decision is being changed here. We need to uh, append B into the string. We need to push that B into the string, not A. So we need to pop back that A first and then push this B. So I hope you understood backtracking from these two examples very clearly. And we will look at one more example. This is to the problem here is to generate all binary strings or bit strings, whatever it is, of size n. So what is the question asking us to do is, if we are given a size 3, you need to generate all the possible binary strings of size 3, 000, 001, 010, 011, like that, 100, 111, something like that. So you'll get 8 values, right? 2 cube. You need to generate all these bit strings. So how can you do that? Here also, where comes the idea of recursion? You have decisions, right? See, here you can choose 0 or 1. Here you can choose 0 or 1. Here also you can choose 0 or 1. You have choices and decisions to be made. So this is a problem of recursion. And when n is less than 1, when n is less than 1, what does that mean? It means you are not left with any decisions. All the decisions are taken, because if n is less than 1, it means n is equal to 0. If suppose n is equal to 0, what does that mean? You are left with no blank. That means, see, all the three decisions you have taken. So then n becomes 0. In that case, you need not take any decision, and you need not proceed further for recursive calls. So you can just push whatever you got into the output and return back to the parent function. So if you are asked to print all these bit strings, so you can just directly use printf string, and that is a if here I am assuming a to be a global variable, be just above the function I have defined a string a of length n. In that case, what we can do? See, if we are asked to do this for a size of 3, then what we will do is, first we will put 0 at the last place. Okay, a of n minus 1 is 0. Then we are calling the same function recursively on these n minus 1. What does this recursive call do? This will take all the decisions to be taken in these two positions. So we are fixing this thing, and we will get all the combinations with ending with 0. We will get all the combinations ending with 0. Okay. So then what we need to do? In this case, we will be getting all the combinations ending with 0. Then you need to change this to 1, because there can be 1 at the end position also. Last position doesn't only need to be 0, it can also be 1. So in this case, you will just make the a of n minus 1 to be 1, and again you will call binary of n minus 1. And what does this do? This will return all the different combinations of smaller input, like other two blanks. So in this case, you will get all the combinations that are ending with 1. So all the bit strings ending with 0, all the bit strings ending with 1. That means you have already found all the bit strings. Problem is done. This is how recursion works. And actually here we are not doing the backtracking which we have seen in the previous two problems. We are just changing the value. This is also considered as backtracking only. We are not reverting the changes back, but we are changing the value itself to a new value. We are just overwriting it. Overwriting it is also a part of changing, right? We here also we are just modifying the value which was done in the previous recursive call. Okay. So this is all about backtracking. Now let's move on to greedy algorithms. Greedy, it's a algorithmic paradigm. It's a paradigm just means it's a technique. Like you can tell it as a technique. Greedy algorithms. See what it is basically is it builds up solution piece by piece, always choosing the next piece that offers the most obvious and immediate benefit. In these cases, we will always choose the one which is better and best at that particular moment. That means greedy algorithms will not work always because every case, choosing something which is best at that particular moment may not be best at the end, right? We don't know about other cases. What will be in the future? We don't know it. So choosing, see, if you do whatever you like at the moment, it may not be good. So greedy algorithms is also the same. So greedy algorithms cannot be applied for every problem because in these things we will just choose something which is locally optimal, and it will be only correct when locally optimal turns out to be global solution. When local optimal solution itself becomes the global optimal solution, then greedy algorithms will be working. And let us look at some problems. Like in see, this greedy algorithms is similar to in mathematics. We have seen something like local maxima and global maxima. See, what we do is we will just assume that local maxima itself to be global maxima. And how do we know whether greedy algorithm can be applied or not? We can just check for few test cases. Like if you can take some inputs and just check it. If you find any contradictory case in which your algorithm is failing, then it means that greedy algorithm cannot be applied on that problem. Now let us look at the very famous problem, fractional knapsack. Fractional knapsack problem is all about, uh, see, we will have an knapsack and we will be given with some items, and for each item, weight and the value will be given. So we need to select some fraction of that, or you can select the entire object and put it into the knapsack. And our knapsack has a capacity. You can't exceed that capacity. You just need to fill that you need to be within the limits. It's limited. You can keep whatever you want. And one more task which we have to do is to maximize the profit. So this is the problem. So what we need to do in this question is, see, in this case we are given with three elements. I mean three objects, and A has a weight of 10, B has a weight of 20, C has a weight of 30, and values are given 60, 100, and 120. And the capacity of this bag is 50. So you can put entire object A, entire object B, and only 2 by third of the object C. This is fractional knapsack. This is called fractional because you can just choose a fraction of an object, like 2 by 3, 1 by 3, or 1 by 2. Any such fractions you can choose. So now let's moving on to solving this question. How can you solve this question? Like, to maximize profit, what you can do? You can take an object which will have the maximum profit, but weight is very less. So we can take profit by weight ratio because we need to take it in a fraction. We are allowed to take fractions, right? So what we can do is we can sort all these objects by profit by weight ratio. We need to calculate profit by weight ratio for each of the item. Then what will be the profit by weight ratio for the first case? It is 6. And for B, it's 5, 100 by 20. And in case of C, it's 4. So what you can do here is, this is giving maximum profit per unit weight. Per unit weight, this is giving maximum profit, isn't it? This is what profit by weight ratio means. See, to maximize profit, and we are also having limited weight. So what we can do is, per unit weight, which is giving maximum profit. Try to take that as much as possible. So, how much quantity of this we have? We have that one, I mean, one full object is there. So, what is its weight? 10. So, take that completely. So, you will have a profit of 60 from that, and your weight will be subtracted by 10. Okay. Then, what is the highest among these two? 5, right? So, now what is the capacity? It's 40 because already we have taken a weight of 10. Now we are left with 40, and now you can take this because its weight is 20 and our capacity is 40. You can take this completely. By the way, we just have one object of all these things. I mean one item of all these objects. Okay. You can't take two, three objects of A, B, C. So now you will take that, and you'll be left with 20 capacity, and your profit will be increased to 160. Now you are left only with 20 capacity, and this has a weight of 30. So how much you can take? You can take only 20 kgs of this C. So 20 by 30 into 120. How much is that? 2 by 3 into, it's 80, right? So you will add 80 to the profit, and your profit becomes 240. This is the maximum profit you can get. In this case, what we are doing is we will be taking the see, to maximize profit, just think of it. How can you maximize the profit? You can take maximum value. You need to choose an item such that it gives maximum profit at a minimum weight, right? So to do that, you can calculate profit by weight ratio, because per unit weight, if it is giving a large amount of profit, you can take that only. Why should you choose this object which is giving lesser profit with more weight? So you will calculate profit by weight ratio for each of the objects. First, you will take whatever will be the maximum amount of A you can take, that much you will take. Okay, that is the local optimum. So here the way, see, the ratio is highest for the object A. So what we are doing, we will be taking whatever is the maximum possible uh, value we can take from A, that much we will take. That is what we are doing, right? So this is called choosing local optimum. We are taking the local optimum. This is A is the local optimum currently. That is why we are taking that as much as possible. Then we will go to B and C. And in these two, which is the local optimum? B, right? B has the higher ratio. So we will be choosing B. And then we will choose C. Choosing the local optimum itself becomes the global optimum. So this is what greedy algorithm is. This fractional knapsack is a greedy algorithm. The algorithm which we use here, like calculating the profit by weight ratio. This is a greedy algorithm. So hope you understood the problem. And by the way, the 240 is the maximum value you can get. You can't get more than that. So that itself is the global maximum. Moving on to the next problem. This is also one of the very, very famous problem on greedy algorithms. This is called activity selection problem. And in this case, you are given n activities with their start and finish times. Select the maximum number of activities that can be performed by a single person, assuming that a person can only work on a single activity at a time. So at a time, a person can work on single activity only. You can't do two things, multiple things at a time. And you are giving start and end times. By that, you need to select the maximum possible activities you can do. Okay. See, 130585. Let me just write down this. 130585, and End times are 246,799. 246,799. See, an activity is starting at 1 second and ending at 2 seconds. This is this starts at 3 seconds and it's 4 seconds. Like whatever is the unit, maybe hours or minutes or seconds, whatever it is, we need to select maximum number of activities, and this is starting at 0 and ending at 6. So what you can do is you need to select maximum number of activities. What will be the maximum here? What can be the maximum? You can select these two, and now you can't select 0 6 because you will be doing this activity from 1 to 2 seconds. See, this is like a number line. You need not see, you should not collide among activities like 0 1 2 3 4 5 6 7 8 and 9. First activity will be from 1 to 2. Second activity will be from 3 to 4. And third will be from this 0 to 6 and 5 to 7. Then 8 to 9. 5 to 9. You need to select the maximum number of activities. What you can do? This is the maximum number of activities you can select, right? Isn't it? These four you can select. If you select this, you can't select any of these three because they have collisions with this. Similarly, if you select this, you can't select in these two. These two can't be selected, right? So in this way, you need to select maximum number of activities. So in this case, what we can do is we can sort the activities according to their end time, because this activity is taking lot of time. This started earlier and is ending very late, so there is no point of choosing this activity. You can choose activities which are ending faster so that we can select maximum number of activities. So that will be the greedy algorithm, right? That will be the greedy choice. You need to select something greedily at that particular moment. So greedy algorithms are just not, see, these are not standard algorithms. Algorithm varies from problem to problem. Whatever will be the local optimum in that problem will be chosen there. So this is not something which is standard like recursion and backtracking. So here, like what I said, you need to sort all these activities according to their finishing time so that you will be able to select next activity which has the minimum finishing time, and you'll be able to select maximum activities. And we will always choose the activity which whose finish time is least among the remaining activities and start time is more than or equal to finish time of the previous selected activity. So what you will do is you will just sort all these things. You will just sort these by finishing time. By finishing time, you need to sort. So I think this array is already in the sorted order. All these are in the increasing order. So this itself is the sorted order of activities given. So first activity you will select, and just check whether start time of the next activity is greater than the end time of the previous activity, because this is, if this is more, you can't start this activity because you can't do two activities simultaneously. So 2 is less than 3. So first activity ended, then you can do the second activity also. And now check whether 4 is less than 0 or not. No. So you can't pick the third activity. Now you move forward, go for the fourth activity. 4 is less than 5. Yes, you can pick it. Now 7 is less than 8. You can pick it. And this you can't pick because it's greater. 9 is greater than 5, right? So how can you pick this activity? So the answer we are getting is 4. This itself is the global optimum, global maximum. You can't
choose more than 4 activities. This is how greedy algorithm works in this activity selection problem. And these are the codes for these two questions. In the first case, I mean for the fractional accept, this is the code, and for activity selection, this one. In case of fractional knapsack, I have just taken a structure. You know it in the C programming already. It is the same with the C++ also. So we are declaring two variables, value as well as weight for each item, and item array is created which will store the various items and total capacity as well as the number of items available. And then we will just sort it according to the comparator function. We will use a comparator function that will just define how to sort the array. We can use comparator function. We can see generally sorting will be done. If it is a vector, sorting will be generally done, but here it's a array of items. So in this case, each item has two properties, value and weight. So you can sort them by value, or you can sort them by weight, or you can sort them by any other function. You need to specify that function, right? So that is where these comparator functions are used, something like CMP, whatever you name that comparator. It's just your naming, CMP. It doesn't mean that it should be CMP always. So see, we are defining it to be, we are just calculating R1 as A dot value by A dot weight, value by weight ratio for both the items, and R1 greater than R2. This means all these elements will be sorted according to the, in the descending order. Right, we need to sort the greater one. So we need greater one to be on the front. So we need sorting to be done in the descending order. So we are defining comparator to be R1 greater than R2. And what is this R1 and R2? A dot value by A dot weight will be R1, and B dot value by B dot weight will be R2. So after that, we will just maintain a current weight, because we need to verify current weight whether it is exceeding the item weight or not. So to do that, we are maintaining a variable current weight is equal to 0, and also maintain a profit variable, initialize it with 0, then traverse over all the elements in the item array A. Then if current weight plus the weight of that is less than or equal to capacity, that means if current weight, what is this? Whatever we have chosen till now. And if you can add this also, like if you are able to add array of I dot weight, it is, if it is still less than or equal to total capacity, then you can add it completely, you can add the full object. So you just add it to the current weight, and also add this value to final value. Okay, otherwise if you cannot add this entire object, then just find out the capacity which is remaining. See, int remaining is equal to total capacity minus current weight. So whatever is the remaining, you can add that much fraction into that, and that much fraction will be the profit. So that fraction into value will be the profit of adding that particular item. So this is the code for fractional knapsack. And coming to the code for activity selection problem, here we are just defining a vector of pair of int. So you have already seen the use of pair in the STL part. So we are maintaining a pair of start time as well as end time. So we are storing all these pairs in vectors, in a vector. See, this vector contains pairs of start as well as end times. So then you will sort this vector, and after sorting, you just need to check whether the current v of I dot second is greater than the x. What is x? X will be the activity selected in the previous case. So if it is greater, like what I have explained here, that is what it is. See, If this is greater than the previous one, then you can add this to the answer. Otherwise, you can't. So that is what we are doing here. So now let's move on to the next problem. Minimum sum of absolute difference of pairs of two arrays. See, here we are given, in this problem we are given with two arrays A and B of equal length, and the task is to pair each element of the array A to an element of array B such that the sum of absolute differences of all the pairs is minimum. So what you have to do is you need to pair each element of A to each element of B so that the sum of absolute differences is minimum. So how can you do that? That means you are given an array, like suppose if elements in this array are like 2, 4, 7, 5, 1. And in array B, if elements are 7, 8, 12, 11, and 3. If you are given this array, from here you need to pair each element to one of these elements. And our task is to minimize the sum of absolute differences. Okay. How can you get the minimum sum? These difference should be minimum. That means these two should be as close as possible, isn't it? Then only you will be getting the minimum sum, right? To get the minimum sum, what you will do? To get the entire sum to be minimum, you need each difference to be minimum. So in order to get each difference, what you can do? You can just sort both the arrays. So see, in this case, the possibility where you can get minimum sum is by sorting 1, 2, 4, 5, 7, and 3, 4, 8, 11, 12. Now calculate the sum of absolute differences. 2, 4, 6, and 5. 11 plus 8, right? How much? It's 19. So just try any other combination. You can definitely get a sum of greater than or equal to 19. So this will be the minimum. See, now suppose if we pair these two, what will be that? 6. And if you pair these two, it's 8. If you pair these two, it is 4. And if you pair these two, it's 2. And if you pair these two, it's 3. 2 plus 3, 5. 9 plus 14, it's 23. Whatever you take, whatever the pair you take, definitely the sum will be exceeding this, or there might be a case where the sum equal to 19 also in some cases. So, but still this will be the minimum. This will be the minimum sum. So what we will do is we will just sort A and sort B, then calculate the absolute difference among these two, and that will be giving us the minimum sum. So this is the greedy algorithm here. Now coming to the fourth problem on greedy, buy maximum stocks if I stocks can be bought on ith day. So in a stock market, there is a product with infinite stocks. The stock prices are given, and array is given which denotes the price of stock on that particular day. There is a rule that customer can buy at most I stock on the ith day. If a customer has k amount of money initially and find out the maximum number of stocks a customer can buy. So he has an amount of 45, and these are the prices of I stock on that day, and he can buy I see at most I stock on ith day. So on first day, see, indexing starts from 0, but see here it's a one indexing for one type indexing. So uh, see, because the day cannot start from 0, so we will use one indexing here. So first day we can buy only one stock, and the price will be 10. On second day, we can buy two stocks, price will be 7. On third day, you can buy three stocks and the price will be. So in this question, in order to maximize the number of stocks a customer can buy, see, we are asked to find the maximum number of stocks a customer can buy. So what you need to do, you have to calculate the maximum number of stocks. So when can you maximize the number of stocks? If the stock price is less, right? So in case the stock price is less, you will be able to maximize the number of stocks. So we will sort this array by we will just first initialize a vector of pairs which will store stock price and day, and we will sort them according to the stock price. So whatever uh, day is having the minimum stock price, on that day whatever will be the maximum amount of products we can buy, you will buy that many products. Okay, suppose here 7 will be the uh, least price. So on second day you will be able to get two stocks, so you will buy both of them. So then you will be spending 14 rupees, and you will be left with 31. Then the price is less on first day. On first day you can buy only one, so you will buy that one stock and you will be left with 21. Till now you have bought 2 plus 1, 3 stocks, and you are still left with 21 rupees, and on the third day you have price of 19. You can buy 3 stocks, but your capacity with your capacity you can just get one of them. So you can buy at max 4 stocks in this case. Okay, this is how algorithm is working in this case. This is the greedy choice we can make. What else can we make? In order to maximize the number of stocks, what we need to choose? We need to choose the stock price. We need to make the stock price to be minimum. So we are buying on the day which has the least price. So we will get maximum number of amounts which we can get from that day. So we will spend maximum amount on that particular day, and then so that we will be getting maximum number of products, isn't it? If we spend more amount on the day which has less price, that only will be the maximum. That is the local maximum, and that is creating the global maximum here. So see, if we have R rupees remaining till now and the cost on this day is C, and we can just buy L products on this day, then what we will do is our algorithm will be defined like this. So on that day, what can you purchase? Minimum of L comma R by C. See, C is the cost and R is the remaining amount. So if R is the amount, how many products can you buy? R by C, right? And we have also one more condition that we can buy only L products on a particular day. Suppose if it is L, so if whatever will be the minimum of these two, that only you can buy. If L is 2 and with the remaining amount you can buy 3, but it's not possible. You can't get 3. You can only take 2 because you are restricted to choose at max, at most, 2 products on that particular day. So whatever will be the minimum of these two, that only you can take. And in our case, we have remaining amount to be 21 previously, and on that day cost is 19. So what is this? It's 1. If we are considering just the integer, it's just 1, right? And what is the L on that particular day? It's the third day. So you can choose 3. But can you buy 3? No, you can just buy 1 because this is just 1. So whatever will be the minimum among these two, that only you can purchase. So on that purchase, on that, see, total purchase on that particular day, P is equal to minimum of L comma R by C, and then subtract the cost. If you have bought P products, then what will be the remaining amount? Remaining amount R is equal to R minus number of products into cost on that particular day, that is C. So I hope you got it. And now let's move. Just check it, check it, check the code. It's nothing. There is nothing new in this code. You just go through the code once and keep trying. Solve some more problems. Then only you'll be getting idea. DSA is something which you can get only through practice. Otherwise, you'll not be able to solve. Keep practicing. You will definitely able to get problems. Understand how it's working. Slowly, you will be getting problems. Okay, now let's go to this thing that I have already told you in the starting itself that greedy algorithms doesn't always work and it gives correct only where local maximum turns out to be global maximum. This is what I have told in the starting itself. And now let's take an example where greedy algorithm fails. See, to make this problem is a very famous problem, coin change problem. I think you will get to know this problem in the session 4 where you will study dynamic programming. This problem is generally solved using DP and we will just see why greedy algorithm fails here. See, this problem is to make change of n rupees using the given denomination using minimum number of coins. See, we will be given with the denomination. Like you need, suppose if you are asked to make something like 25 rupees and you are given some denomination, like you have 1 rupee coins, 5 rupee coins, 10 rupee coins, 20 rupee coins, and you need to make 25 rupees using this denomination with minimum number of coins. So how can you do that? You can select one 20 rupee coin and one 5 rupee coin. Two coins are needed to make this change. And if you can do it in multiple ways. You can select two of these and one of these. That will be three. But we are asked to find the minimum. So this is the minimum. So in this case, greedy algorithm fails. In this case, what can be the greedy algorithm? Just think of it. To minimize the coins, to minimize the number of coins, we can always select the highest denomination which is less than or equal to n. That is what we have done here, right? This is 25. So I have taken 20. 20 is less than or equal to 25, isn't it? So I have taken 20 and I am left with 5. I have one more 5 rupee coin. So with two coins, I will be able to make 25. My task is done. But will this always work? Here comes an exceptional case. This is where the greedy algorithm fails. So in this case, in this coin change problem, you cannot use greedy algorithm because if this is the denomination, see the denomination 1, 5, 10, 20, 25, 50, and if you have to make, if you are asked to make a change of 40, what will be the output? Output will be 25. We need to select the highest denomination less than or equal to change. So 25 will be the highest because 50 you can't choose. Then what will be the next? We 25 is done. So we are left with 15. So less than or equal to 15, there is 10. So 25 will be selected, 10 will be selected. Now we are left with 5 rupees. So 5 is available. So we will select that 5. So 3 coins we are using. But the optimal solution is to select two 20 rupee coins. This will be just taking two coins, but our greedy algorithm gives an answer of 3. So here greedy algorithm is failing. So this greedy algorithm which I have written cannot be used in this question. Hope you understood this. Now let's move on to the last topic of this session, hashing techniques. Hashing is a technique or process of mapping keys and values into a hash table by using a hash function. In this hashing, we will just use a hash table. Hash table, it's nothing but just a, see in C++ STL, we have already learned map. So that is very much similar to hash table. Actually, map, unordered map itself is implemented using hash table only. See, in this, there is a hash function through which we will map each of these keys into that table so that the retrieval will be faster. See, this hashing technique is generally used in many places, like even in databases, hashing is used to make the searching faster. So let's move on. In this diagram, you can see a hashing function x modulus 10. Modulus 10 is used. That is a hash function which we can use. Yeah, see, hashing it's not that much used in DSA. You can directly implement it using an ordered map. So we will directly use those things. We will not go much deeper into these hashing techniques. And this is not generally used in DSA. This is something which is more theoretical and you can learn it in your data structures course. Now let's move on to problems. Let's solve two problems and end this session. First problem will be counting pairs with given sum. Here we are given with an array of n integers and an integer k, and the task is to find the number of pair of integers in the array whose sum is equal to k. See, you are given n integers and an integer k, so number of pairs whose sum is k. Suppose if you are given an array like 1, 2, 4, 3, 6, 7, and you are given k value to be 5. So you need to find number of pairs such that their sum is 5. So 1 plus 4, it's 5, right? And 2 plus 3, 5. So we have two such pairs whose sum is 5. So in this case, you can use an unordered map. How you can do? How can you use that? See, initialize an unordered map and set the count to be 0. Now, while before inserting every element into the map, just check that k minus this element is already present in the map or not. See, first we will traverse over each element in the array. Now we will find k minus arr of I. So k minus 1, what is it? 4. So 4 is already present in the map or not. M dot find is not equal to m dot n. It means, see, what is this find function is doing is actually, if it finds that value, it will return an iterator to that position, or else it will return an iterator to the end of the map. So it will return m dot n. So it is not equal to m dot n. What does that mean? It means it found an element. It found that particular element in the map. So while before inserting this one, we will just check whether 4 is present in the map or not, because 5 minus 1 is 4. So 4 is not present. So we will just, this if condition is false, so it will not execute it. And we will just push this one into the map. Now come to 2. Then we will just check whether 3 is already present in the map. It's not present. Now just insert 2 into the map. Next, we will find whether 1 is present in the map or not. Yes, it is present. So we will just increment the count. We will increment the count to frequency of that 1. And then we will just check whether 2 is present in the map or not before inserting this 3. Yes, it is present. So see, we found 1, whatever is the frequency of this one, that many pairs you can make. Because if you have multiple ones, if you have two ones in the same array, what you can do is you can pair up these two, or you can pair up these two. So if its frequency is 2, you can add directly 2 to the count, because you can make this pair as well as this pair. So whatever is the frequency of that element, we will add that to the count. Count plus is equal to, means count is equal to count plus map of k minus arr of I. That whatever is the frequency of that particular element, that we are adding to the count. So this is the code for this problem. Now let's move on to the next question. Maximum distance between two occurrences of the same element in the array. See, here we are given an array with repeated elements, and the task is to find the maximum distance between two occurrences. See, unordered map is mostly used in these cases, like when we want to store frequency, or when we want to store occurrences. In these cases, we can mostly use this unordered map. So in this question, we will be given with an array, and that array will have some duplicates also. And we have to find the maximum distance between two occurrences of the same element. Like if we are given an array like 1, 2, 3, 2, 3, 4, 5, and 1. So what will be the maximum distance between two occurrences? First one is occurring here and the same one is occurring again there. So that will be the maximum distance. It will be 1, 2, 3, 4, 5, 6, and 7. 7, right? So that will be the maximum distance. So how can you solve this problem? You for this problem, you need to store the index of a particular element. So for storing the index, what you can use? You can use an map. So for one, first we will push it into the map. Before pushing it, we will just check if this is the first occurrence of the element or not. If yes, if that is the first occurrence, see, in this case, maximum distance we will be able to get when we just store the first occurrence. We need not store the middle occurrences. See, one can also occur here. So if you consider this thing, that will not be the maximum distance. So you can get maximum distance only when you consider the first occurrence of the element. So whenever an element is occurring for the first time, then you need to push it into the map. To find the maximum distance between two occurrences, we need to store the first occurrence in the array. So for each element, we will just check whether this is the first occurrence or not. How will you check that? If map.find is equal to map.end, that means you did not find that element in the map. That means this itself is the first occurrence of that element. It did not occur before this. So in that case, you will store map of array of I to be I. That means you are storing that particular index in the map. Else, just update the maximum distance to be max of maximum distance and I minus the current index minus map of that element. I mean, see, if this is not the first occurrence, like suppose if you have arrived at this place, this is not a first occurrence of 1, right? So 0, 1, 2, 3. So here what we will do is we will just find the max of maximum distance comma I minus this index 3 minus its first occurrence. What is the first occurrence of 1? Map of ARR of I. What is that? 0. So 3 minus 0 will be 3. So we will store max of 0 comma 3 in that maximum distance variable. So that will be updated to 3. Then when we arrive here, again you will update, again here you will update, here you will update, and again when you arrive to this position, you will update this with the this difference, right? This is the new distance and that will be the maximum distance. So that will be the answer in this case. So this is the use of unordered map, and hashing is nothing but it's just uh, storing a key value pair using some hash function. So this is the end of our session. So I'll recommend you, all of you, to solve all the problems we have discussed in this session. You just try all these problems on your own without seeing the code. Just try to code, and also you can solve problems topic by topic. First, you can start with recursion and solve 10 to 15 problems on recursion, and you keep solving until you get some concept and command over it and you feel comfortable in that topic. Keep solving. For DSA kind of questions, you can use lead code or geeks for geeks, and for competitive programming you can use that code chef code forces, where the questions will be more math oriented and they will be more logic oriented in the initial stages, and later there also you will be using algorithms, various algorithms of DSA. So yeah, thank you.